Don't you hate it when you're charging your lithium-ion battery but you can't tell if it's operating at unsafe conditions, like if it's getting too hot? Well, so do I. The perfect solution would be a product that cuts power to the charger and stops all that unsafe charging. So that's exactly what we built. A system that measures voltage, current, and temperature of a battery, and if unsafe operation is detected, it cuts power to the charger and stops operating. Ladies and gentlemen, the Smart Battery Management System.
Here is a high-level block diagram for how our project is going to work. The charger will be hooked up to the positive and negative terminals of our lithium-ion battery. This connection will be fed directly into our battery interface board, where a blue LEM current sensor will monitor the current of the battery. This information will continue into our main BMS board, where all the measured voltage, current, and temperature readings from the battery will be taken. These readings will feed into an analog to digital converter, which translates the data to a digital signal that can be read by our Raspberry Pi. The Pi will be the one to determine if our battery is operating at safe and stable conditions. If the Pi deems the battery to be unsafe, it will send instructions to a relay to open up the connection. This will cause the circuit to break and stop the flow of power. Once it is safe to resume charging, the relay will close and power will be restored, allowing the battery to continue charging safely. Here is the battery interface board with a blue LEM current sensor. The LEM sensor's job is to sense the current of the battery. Here we are testing to make sure that it can detect an adjustable voltage through a 100 watt 4 ohm resistor. Up next is our BMS board. Here we are testing our voltage differential amplifier, which consists of an op amp and a negative feedback loop. Its job is to take whatever the input voltage is and attenuate it down to a range that can safely power our PCB, which is no more than 5 volts. Another key component of our BMS board is the TMP36 temperature sensor. Its job is to sense the battery's temperature and relay that information to an analog to digital converter, along with all the other battery sensor readings. Here we are placing our 100 watt resistor on the temp sensor since it gets pretty hot when in use. As the resistor sits on the sensor, its temperature rises from its regular room temperature rating of about 750 millivolts, and once the resistor gets removed, the sensor cools off and the voltage level decreases. Here is a relay which acts as a kill switch whenever unsafe operating conditions are detected from the sensing circuits. Here we are proving that when the relay is powered, 120 volts AC power can flow from the wall through the circuit. Once wall power gets removed, the relay opens up and breaks the circuit to stop the flow of power.
And here we have the UI. It has our measurements for current, voltage, temperature, and a plot of the state of charge, all updating in real time. As we increase the voltage and current, the state of charge changes and the plot updates. And here we can see the displayed measurements for voltage, current, and temperature, all updating in real time.
That concludes the how and why of our project. We burned up some parts, and the project underwent a few revisions. But with the guidance of Dr. Munshadi and our mentor Vidya, we all came together as a team to put together a project that tested all of our engineering knowledge. This project has been one of the most valuable learning experiences we've obtained throughout our time here at STSU. Thanks for watching, and we look forward to demoing our project for you on Senior Design Day.